All right. So now what we're going to do with the drag force is we're going to see what happens at the very beginning with an object falling versus the very end. All right, so here's what we're going to do. We're going to say that we are dropping an object, say maybe the coffee filters that we saw a moment ago, off a cliff. We're going to say that we're really high up in the air, and we're going to drop the object. I'd like to know what the acceleration is going to be at the very beginning. Well, if I were to draw a free body diagram of my object, we're going to have at any given point force of gravity, mg down, and since it has a set mass, let's say that we've got a mass. Let's not use the coffee filter, shall we? Let's instead use a tennis ball. We'll say that it has a mass of maybe 0.1 kilograms. It's actually a little bit big for a tennis ball, but it'll make our numbers a little bit easier. So you might think of something, maybe a baseball. A baseball is something like 150 grams. So this would be a lightweight baseball. And I'm going to drop it off the cliff here. Now we're also, as this thing falls, we're going to end up with a drag force that points up. But the important thing is this. We're going to say that I'm dropping it so it starts with an initial velocity of 0 meters per second. So at any given point while this thing falls, my sum of forces in the y will look like this. The drag force, which is up, so it's going to be positive, minus the force of gravity, mg is down, so I'm going to do negative, equals ma. Now, one of the things that we might actually need to incorporate in here is that the acceleration is going to be negative. So I'm going to put a negative sign here. In short, for a lot of this, you end up with the drag force is going to be up, force of gravity is going to be down, and at pretty much every single point, the force of gravity is going to be bigger than the drag force, so that means our acceleration, our net acceleration, is going to be downward. I'm going to keep track of that with a minus sign there. Since we know that the acceleration will be down, I'm going to go ahead and put that in there. The one exception to that is when we reach terminal velocity, like we talked about, these two are going to be equal to each other, but then the negative won't matter because it's going to be equal to a 0, and we could just divide the negative out anyway. Another common way to deal with this, even though it's not the way that I'm doing it, is to have the downward direction be the positive y. We can relabel down positive y whenever we want to, and up becomes negative y. If I were to do that, then it would be positive mg minus the force of drag equals positive ma. Once again, the negative here on this side is because I know that any acceleration that I have for this problem is actually going to be downward. That may or may not be useful for what we're about to find here. However, when we look at the calculus side of this in just a minute, that will also actually be something that you want to keep track of. All right, so let's find out what the acceleration is at the very beginning. And here's one of the things that becomes problematic because we can't actually apply kinematic equations on this like normal. And the reason why is the kinematic equations that we learn about in class only apply when acceleration is constant. And as we're going to find, the acceleration changes. We're going to have a different acceleration at the very beginning than we do at the end, which means it's going to be very difficult to apply kinematic equations onto this. All right, let's find our initial acceleration. Well, initially, our velocity, I apologize, one other thing we need to bring in here. Since this is an object that's going to be falling through the air, I'm going to say that the force of drag is going to be equal to b times v squared. And I'm going to give you some additional information. Let's say that b is equal to 2 with appropriate units, which would be Newton per meter per second squared. Or Newton second squared divided by meters squared. In short, I need something that multiplies with the v squared and gives me a force out. So, in case we haven't talked about that, that's something to keep in mind. If I want to multiply it by meters per second squared, then this needs to have units of newtons divided by the quantity of meter per second squared, so that the meter per second squared cancels out, leaving me with newtons. Regardless, let's just say that the value of b is going to be 2. We're just going to call it 2. That should be easier. All right. At the very beginning, our speed is 0, so when I put in 0, let's see, I'll have Fd at the beginning, which will be b times v naught squared minus mg equals negative ma naught. we see that this is 2 times 0 squared minus 0.1 times 9.81 meters per second squared. Oh, I left the units off of everything else, so I might as well keep with that. This would be kilograms and meter per second squared. You'll notice that this also comes up to newtons, equals negative 0.1 times our initial acceleration. Well, this is a whole lot of 0, so we end up with the following. Negative 0.1 times 9.81 equals negative 0.1 times a naught. The magnitude of a naught is going to be equal to, let's see, well, I can just divide by a negative 0.1, and we end up with 9.81 meters per second squared. Now, it's technically negative 9.81 meters per second squared. The reason our equation didn't give us that is we already stated that it was going to be negative by putting in that negative there. You can imagine if we didn't know it was going to be negative, we'd ignore that, we'd divide this by 0.1, and this negative would give us a negative 9.81. The reason that this just says 9.81 and not negative is because we already asserted that it was going to be a negative number, and that's where that negative shows up. Now, you wouldn't necessarily need to do that, but here we find that the initial acceleration at the very beginning, for that first instant before it starts moving, is actually going to be free fall. It'd be 9.81. Let's find out what the terminal velocity is going to be. Let's call that V. A lot of times it's actually marked as VT, but I don't necessarily like that notation. So let's just call it V1, the ending velocity, our very final velocity. Now, it's very common to use VT, but as we're going to see with the calculus side of this, VT is usually something where it looks like V as a function of t. It's also sometimes common to use a capital T, but there are other reasons I don't really care for that. So for the purposes of this video, we're going to call it the final velocity, V1. All right, well, when that happens, our terminal velocity occurs when the force of drag is equal to the force of gravity. So my sum of forces is still the same as I saw before, Fd positive, because it's up, minus mg equals negative ma final. All right, well, let's see what we end up with. Here is where Fd is going to be equal to mg. mg minus mg equals negative ma final. These two actually just become 0, and we end up with 0 equals negative ma final, where m is 0.1 kilograms. I divide both sides by 0.1, but it doesn't actually matter. We find that our final acceleration is 0 meters per second squared. When these two forces are equal and opposite, we end up with no net force, no net acceleration. Newton's second law in action. Great. I wanted to find the terminal velocity, but now I know at this point it's not going to speed up or slow down anymore because we have an acceleration of 0, which means my drag force is going to be equal to mg. That's what we said would be the final result of this when it finally reaches terminal velocity. Well, since my drag force was bv squared equals mg, if we have the drag force equal to mg, it's not just v, it's actually our final velocity. It becomes our final velocity, our terminal velocity, when the drag force is equal to the force of gravity. So we can find our terminal velocity pretty quickly by taking the square root of mg divided by b. All right, so we've actually got some numbers here, so let's go ahead and do that. We've got 0.1 times 9.81 meters per second squared, all divided by 2 with some units. I'm being fast and loose with units. Give me just a moment. I have misplaced my calculator. Here we go. 9.81 times 0.1. It's about 0.981. Great. Divided by 2. And I take the square root of this. I have laughably ridiculous numbers because I just threw 2 at the problem. And we find that the terminal velocity for our baseball is a paltry 0.701 meters per second. That's not remotely realistic. Now, the reason that we ended up with that is because I got lazy and gave us a B that I, well, just admittedly, made up off the top of my head. Let's go about this a different way. Let's use something a bit more realistic. Now, I didn't actually prepare as much as I probably should have for this, but feel free to go through and use something like Google and ask what the terminal velocity for a baseball is here near the surface of the Earth. I'm going to take an estimate, though, and let's say that the terminal velocity for a baseball, a real baseball, there's that VT, I'm going to switch it over to V1 here. Let's say that it's something like 200 miles per hour. I know that Major League Baseball pitchers usually can pitch a fastball at about 90 to 100 miles per hour, and I don't know how much it will slow down a little bit, but I think that that gives me kind of a ballpark here. 200 miles per hour sounds like it's probably, if not the real number, at least something far more realistic. So, 200 miles per hour. Let's go ahead and convert this into SI, or 1 hour. I can get rid of the 1 hour by dividing by 3,600 seconds. Hours cancel out, and then I get rid of the miles. 1 mile is 1,609 meters. Miles cancel out, and I'm left with meters per second. So let's go 200 times 1,609 divided by 3,600. It's about a factor of 2, as we've talked about in class, but this gets us something like 89.4 meters per second. Let's find out what the a more realistic value of B is for the baseball. We know that at terminal velocity, the drag force will be equal to the force of gravity. And since we're dealing with a more realistic value, we're going to end up with B of the baseball times its terminal velocity squared is going to be equal to mg. We're trying to solve for B, so B is going to be equal to mg divided by V1 squared. Well, if I put this in, we said about 0.1 kilograms. It's actually about 0.15. I think it's 0.146 is like the regulation, not that it matters. 9.81 meters per second squared, and then divided by the final, our terminal velocity squared, which we just said was 89.4 meters per second quantity squared. Now, when I solve this, I end up with 0.1 times 9.81 divided by the quantity of 89.4 squared. If I've done this correctly, we end up with a laughably small 1.23 times 10 to the negative 4th kilogram times meter per second squared. That is a Newton divided by the quantity of meter per second squared. Those are those units that I mentioned before because they have to work out for the equation to actually work. Here's why we got a laughably ridiculous terminal velocity, because I said that B was equal to 2, which it very much is not for a baseball. This would be a more realistic value for B. Now, that being said, it's entirely possible that we may give you some laughably off-track values for B, depending on what we want you to work on with the mathematics. For a lot of the calculus involved, we may not even give you a number at all. All right, so this is working a little bit with what happens. At the very beginning, when you let go of the object, because it's not moving, the drag force is actually equal to 0, and for that very beginning moment, the acceleration is equal to free fall. But as it starts speeding up, you get more and more drag force on it, and that will reduce the acceleration as the difference in the forces approaches 0. And then eventually, you will end up with the drag force being equal to the force of gravity. It will no longer accelerate, and you will continue moving that object at terminal velocity the entire time. Again, this is the idea behind a parachute, going back to some of the stuff that we had before. The idea behind a parachute is to get a very large area so that your drag force becomes bigger by adjusting B so that it can match gravity at a lower velocity, hence helping keep you alive. Next up, we'll take a look at the calculus side of this and what happens in between. Does it just increase linearly, or what does it do? We're about to find out.